Hello. Today we'll be exploring the applications of Raoult's law. So to begin with, we'll start off with the more simpler concepts, that being dew point and bubble point, and we're going to see how we can get those expressions to solve for them through Raoult's law. And later on, we'll sort of see the more difficult stuff, as you can see on screen. And so let's begin. To begin with, to start off, um, what is Raoult's law, right? So, Raoult's law, I'll sort of just write it out, and afterwards I'll explain what each term actually means. And so we have xi being multiplied by pi sat, and that's equal to yi times p. And so what does every term mean? Firstly, I is simply the number or the component that we're dealing with. So I could be any number up to your nth component. So say we have a binary system. Um, your first component will be labeled with 1, I equals 1. And usually you want to make that your most volatile compound. And then obviously your second compound is number 2, I equals 2. And so what does this x mean? This x here is the mole fraction of component I, so first or second, if we're still sticking to that binary system, in the liquid phase. So x here will denote liquid. Next, we have our pi sat, which is the saturation pressure of component I. And to put it into a sort of more relatable definition, we could say that it's the pure component vapor pressure of component I at your designated temperature. And so that could be end-to-end equation, or simply if you have some other means to get that value that way. So next we have yi, which is the mole fraction of component I in the vapor phase. So that will be our distinction there from x and y. Y will denote vapor and x will denote liquid. And we have this p, which is actually a standalone value, which is the total pressure. And these two terms actually here, the mole fraction of the component in the vapor phase and the total pressure, when actually computed, can actually be simplified to just simply the pressure, or well, the partial pressure of that component. And that'll be useful later on here. And so that's just Raoult's law. So let's move on to bubble point and dew point. So starting with bubble point, what is bubble point? Well, bubble point is the point at which your first vapor bubble is formed, as minuscule as it needs to be. And so there are two scenarios that we can sort of work with in terms of problems, that being the bubble temperature and the bubble pressure. And so let's say you are given a system here, and you are given the temperature, right? So you are given that the temperature is some value. So this is all liquid at first to begin with, all liquid. And let's also say that we're given the mole fractions of each component within the system. And so we can say that the summation of all those, and remember this is Antoine equation, And so the temperature dependency that we have for that, well, we can sort of satisfy it since we're given it. We can just input it into that equation or whatever other means that you have to get that value. And we'll be given the summation of all the partial pressures, which is just the pressure, total pressure. And so then from that, right here, do pressure, not do, bubble, uh, bubble, bubble pressure. And so this pressure value that we obtain from calculating these, which have our given values, which were given, so we can actually calculate it, right? This is the pressure we'd have to set to the system to form our very first vapor bubble. And so just the equation itself is not that difficult or complex, as a matter of fact. And that sort of leads on into bubble temperature as well. And so just to have an expression for it, like I said earlier, the pure component vapor pressure, this PI sat here, is dependent on temperature. And so, and for the case that it's bubble temperature, we don't know our temperature, but we are given a pressure for the system. And so we want to match those pressures, right, to form that first bubble, the external and internal pressure. And so what we would do is sort of have the Antoine equation, right, and sort of control this temperature value until you match the pressure. And you can sort of sub that into PI sat, and you'd have a really complex expression. But I'll actually just leave the expression as this original expression here, and you'll see how we can sort of solve it in a different way without having to sub in the N20 equation or some other different equation into that term to make it a complex sort of looking expression that we'd have to code out later. And so for now, it will simply be also this expression. And that same sort of logic applies to do pressure and do temperature as well. So for do pressure, our system this time will be all vapor. So vapor. And then we're given the temperature as a value. We're given the temperature, and we have to sort of find the pressure at which the first drop of liquid forms. And so what do? Well, we would be given the mole fractions of each component in the vapor phase, right? And we're also given the temperature, so we can sort of calculate the pure component vapor pressures of all those components at that temperature. But we're sort of lost. We have two unknowns here and only one equation. But that isn't true in the sense here in what I'm about to say. So it would not be wrong to say that the summation of the mole fractions of all the mole fractions of all the different components within the system would equal 1, right? So we can sort of write that down. We can say that the summation of all the mole fractions in the liquid phase, let's say, is equal to 1. Because we'll say in the liquid phase here, because it's true for both vapor and liquid, but we need the liquid phase in this case. We can say that summation is equal to 1, and that makes sense. So now we have two equations, two unknowns, and they sort of work out now. So we can actually figure this out. So plugging that back into Raoult's law here, we can say that this is equal to, if we moved everything over, this sat over here, we can say summation again, since this is summation here, that it is now equivalent to this here. I simply just divided this over. And we know that P here is simply a singular value, total pressure, right? So you can move out of the summation. So now we have something like this. And now we can solve for the pressure that we need to form the first liquid drop by simply dividing this entire term over. So we get the inverse. And so we get P is equal to 1 over the summation of the mole fractions of the vapor phase over the pure component vapor pressures. And of course, we can solve for that since we're given temperature. And like I said, um, we'll sort of be using the same expression here for due temperature, but we'll have to be sort of changing our values since we're looking for temperature, a certain temperature that matches with the pressure that we're given. And so how will these look like when coded out into Python, right? So let's do that. And this will sort of give insight on what I mean in terms of the bubble temperature and due temperature expressions and how they are ultimately just the originals in a sense. And so let's move on to that. All right, so here we are in Python Collaboratory. And I have already put in our usual imports that we'll be using here. And so it shouldn't be too unusual for what you've seen before. And so later on here in the video, I will actually be I will actually be using some compounds here. And so I'll sort of import them here now. So then when I sort of create these functions, we have a way to sort of test and see the values that we get. And so I will put in the properties into this p variable of, and we'll actually be working with a binary mixture, which will be benzene and toluene. All right, so let's make our functions for our bubble point and dew point. So to begin with, let's do our bubble pressure. And so what will we need for it? Well, we're given the liquid mole fractions of the components, right? And we are also given the temperature. And what do we want to return? Well, we have written that formula, right? So it is the summation of the mole fractions, right, times the pure component vapor pressures at that temperature. And that's simply it, right? And so I'll put it here. Let's say that our mole fractions of our components will be 0.3 benzene and 0.7 or 30% benzene, 70% toluene. And so let's give this a try, right? So our bubble pressure, we'll take in that array there with our mole components, mole fractions, right, of our components. And let's say we're doing it at 393. This didn't work because I put define there for some reason. And we get 180,000 pascals as our pressure that we have to set it to get our first bubble vapor to form. And so now let's move on to bubble temperature. And this is sort of what I mean by we can sort of do something different instead of having to, we're given our pressure, right? Instead of having to substitute the pure vapor pressure with the Antoine equation or whatever other equation to make our expression messy. Instead, we already have a function, a formula, right? Bubble pressure, where if we input some random temperature, we're given some pressure of that value, right? And we just have to make sure that that bubble pressure matches the pressure that we're given. And so instead of guessing the temperature values to match that bubble pressure with our given pressure, we can simply use a root solver to guess that value for us. And so that's sort of the more simplified way that we'll use instead of having to substitute our pure component vapor pressure with the Antoine equation, for example. So let's do that, right? So in that case, we'll actually have to put another function inside our original function to use the root. And so this will take some vector because that's what root wants. And since temperature is going to be the only thing that will be unpacked from it, we can sort of do V0, not with those brackets, V0, right, to call that one value. So this sort of saves us just one line of code. So we want it to return the bubble pressure. Want that as an array because that's what root outputs it as of x at some temperature. Like I said, that will simply be the first value of the vector minus whatever pressure value that we're given. And so now we can use our root function and put in the equation we just made and put in some guesses, which I will keep it as just standard state. And roots obviously outputs a bunch of stuff. We only want the x portion of it. And the key, it actually, here, I'll just show it to you. And so if we wanted to use it here, so bubble temperature, x, and we'll use the pressure here that we got from bubble pressure to sort of make sure that we did this correctly. And we should get the same temperature value, which we do. And you'll see that it comes out as an array. So if we just wanted this singular value, we could do 0, pull out that value, that one value, and we'll just get a scalar when we run the function for it. And so that's what we get for bubble temperature. And so it's actually the same exact process for the dew point, dew pressure and dew temperature. It's the same exact thing, just using the formula that we, the expression that we developed beforehand. So just running through the thing. Another difference is that we'll be working with vapor mole fractions. So I'll define it up here. I'll just use the same percentages. And let's start with dew pressure. So it'll take in the mole fractions of the vapor phase, and our temperature will be given. Not that. All right, and so it'll return the inverse, right, of the sum of the vapor mole fractions of the vapor phase of the components divided by the pure component vapor pressures at that temperature that it was given. And so we can run this at 393 Kelvin as well. And we get 157,000 pascals. And we get two different values, right? Between bubble pressure and dew pressure. Dew pressure being, once again, the first liquid drop that forms. We can see that they're two different values. And it sort of makes sense for the fact that they're labeled two different things, right? And so let's continue on here with our dew temperature. This time with our pressure that's given. And once again, we'll have to do with the same thinking for bubble temperature. Instead of having to sub in the Antoine equation, we can use our dew pressure to sort of guess it, and then root that guess so that we get the actual right number. And so let's do that. Once again, just using a vector because that's what root needs. And then we return this difference so that we can zero that out, right? This time, vapor phase mole fraction of the components. The only value within this vector, so we can just pull out that first value, right, with that notation, and then we subtract it with the pressure that we're given. And then we simply return the roots of that equation. With a guess, I'll just do standard states. And once again, we just want the scalar value. And so just to make sure that we did this right, we can compare it to the other value that we got for due pressure. So if we put in 157, 108, we should get 393, which we do. And so, as you can see, the functions for these aren't actually all that complicated. Thankfully, with the tools that Python has, we don't have to. We can sort of circumvent the fact, the route that we could have done, in which we had to substitute end-to-end equation into the pure component vapor pressure. So what else can we do now? Well, we can sort of plot these functions and sort of see how pressure and temperature sort of vary depending on our mole fractions within our mixture, our binary mixture. So that's what I'll be doing here next. All right, so now we want to plot out these functions here, right? And so we're going to have two different plots here to showcase the two scenarios where we are either given pressure or temperature, right, for either bubble and dew point. And so you'll notice here that we actually have two different compounds, X or Y1 and X or Y2. So how would we plot the varying mole fractions on the x-axis, whether it be pressure or temperature versus X1 or X2? Well, it's sort of, if we were to put X1 as our x-axis, right, going from 0 mole fraction all the way up to 1, it's sort of implicitly stated that X2 is 1 minus whatever X1 is. So for example, if we were at 0, if X1 were 0, X2 would have to be 1 mole fraction, right? 1 minus 0. And that continues on to whatever X1 value is. And so that's what we'll do for our plots in terms of the x-axis. And so you might notice here, we'll have to use both xi and yi for our plots for our independent axes. And the reason we can do that is because they sort of inherently share the same values. It's just that we interpret those values differently for each case. And so because we do that, we can sort of consolidate everything into one variable and just use that in our coding. So that's what I'll do. So I'll actually get rid of this cell here, get rid of these tests too. And we can sort of say that different variable, let's say z1, is equal to linspace, so that we have equally separated segments for our x-axis here, for our mole fractions from 0 to 1. So if we were to look at z1 here, we can see the different mole fractions for x1 or y1, depending on which one you want to interpret it as. So 0, 10%, 20%. And like I said earlier, z2 is simply the difference of 1 minus that z1 value. So z2, you can see that. And so let's get started on the scenario where temperature is given, the easier one. And so we want to either run a, for most cases, you want to run a for loop to obtain each separate value and sort of add it onto an empty list and then plot that list. But bubble pressure is actually just a summation of the 2 points. And then that result is just plotted. And so we don't actually have to run a for loop for this specific function. And so to sort of, for this scenario, it will be at 393 Kelvin. And so I'll set the pure vapor pressure, pure component vapor pressure. I'll set it at its own variable, so I don't have to type out as much. And so and like I said, it's just a summation of the 2 points, so we don't have to run a for loop for it. So we can say something like this: z1 times psat, the first value, because this holds 2 different values, right? The benzene and toluene. And then z2, or x2, compound 2, toluene in this case, will be multiplied by its pure component saturation pressure, which is the second value within that list. And we should get our values for the bubble pressures at the varying mole fractions for each. I didn't capitalize the L there. All right, and we get those values there. So this is when benzene is at 0 mole fraction, and this is toluene at 1 mole fraction, so 0% and 100%, up by 10% each time for benzene, all the way until it's at 100% benzene, 0 toluene. And these values sort of make sense because benzene is the more volatile compound, so you would expect a higher pressure value, bubble pressure, when it's 100% benzene. All right, so let's start working on our dew pressure, the other function that we can actually put on this graph. And so, like I said earlier, what we want to usually do is run a for loop to run the function and input the value into a list, in which we then plot that list. So let's do that. So we want to start off with a empty list here. And then run a for loop. And this is this is where we can, like I said, interpret the z's as something different for what we need to use it for. So just to sort of differentiate, we'll say for y1 in z1 here, so each value in z1 will be interpreted as y1. Y2 will equal 1 minus y1. Same thing as z2 equals 1 minus z1. And we're sort of reconstructing the y that I had earlier to test these functions, right? But this time as an array with all the different varying mole fractions this time. np.array y1, y2. And now we want to run the function every time it has a specific mole fraction before it moves on to the next one. All right, so we want to run dp of y, right, at temperature. And we want to add this onto the empty list every time it runs through the list, the for loop, I mean. And so list dot And so if we wanted to look at our list for dew pressure, we get that. And so let's plot the two, right? So fig equals make subplots, and we'll have another column here for the um, dew temperature and bubble temperature stuff. So fig dot add scatter, x will equal z1, y will equal our bubble pressure lists, and then this will simply change the dew pressure. So if we plot that, here's what we get for that. So just to interpret it, I guess, here's our 0% benzene. So that's the pressure value. And then our x2 would be 100% toluene. And so if we were in this section of the graph and we were to decrease the pressure, right, after this line here, this blue one, the linear one, which we would expect to be the bubble pressure, we form our first drop of vapor, bubble of vapor, right? So as we reduce pressure, that was kind of indicative of a liquid section. This would be our liquid section up here and our vapor down here. So if we were to increase, let's say at 40% benzene, 60% toluene, if we would increase the pressure to this value and we would form our first drop of liquid. In that case, until we pass up into this full liquid section. And so that's just that for this graph. And so now let's move on to the dew and bubble temperature plot. All right, so let's get started on our other plot here, which is going to be the dew temperature and bubble temperature, right? Where we're given a certain pressure. And so we'll have the same rundown as what we did for our dew pressure here, where we run through a loop, calling the function to spit out an answer, for lack of a better term, for that certain mole fraction of each component, right? And so we'll be doing the same thing here for bubble temperature and dew temperature. And so first, what I'd like to do is separate this cell, this line of code from the cell that's in, just so that this one can just be our constants, and it's just our pool of numbers, all right? And so our pressure is going to be at 150,000 pascals. And so, like I said, we'll be doing the same exact thing here that we did for dew pressure. And so let's start with bubble temperature, empty list, and we'll do it for x1, liquid, right, in z1. Same thing. X2 is simply the difference between 1 and x1. And then we'll create an array of the two so that we have our two mole fractions for our function to sum. So x1, x2, and now we would just want to call our function at x at pressure that we already defined before, and we want to append it to this list. And so if we want to look at this list now, we see our bubble temperatures. And it makes sense, right? If we were to have 0% benzene, 100% toluene, we'd expect a higher temperature to create that first vapor bubble, as toluene is the less volatile compound, right? And so uh, what we'd be doing next is sort of creating a exact copycat of this cell here, which technically is already a copycat of the one before. And so to sort of clear up some space, we can sort of like reuse this code, because this is technically the same numbers, um, right? These are the same numbers. Uh, we're just putting a different name on them. And so we can sort of use it for the dew temperature as well. And I guess to sort of differentiate the fact that this is a combo sort of usage, we can say XY, 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 this is XY, and then simply this, this will also call the dew temperature function, and but it'll work just as normal. And uh, we can see our list for this, for dew temperature. And just to show bubble temperature as well. Uh, and they are different values. So that shows it worked. And so, um, and of course, we could have done that for this as well. So, um, yeah, but I won't be doing that now since I've already typed that out. And so let's generate this plot. So fig dot, actually, I'll just copy and paste this. And of course, this will go in the second column, so I'll have to put that. All right, and now we just swap these out for their respective lists. And there we have it. And so looking at this, we can tell that obviously increasing the temperature, this right here is our bubble temperature. So once we pass this line, we've made our first drop of our first bubble of vapor, and then passing on to this, we have full vapor, and then obviously the reverse of that. Once we pass this line, we've made our first drop of liquid, and then eventually passing on past this line, we have our full liquid. And so these types of two plots here uh, actually have a name, and they're called a vapor liquid equilibrium plots. In this case, it would be called a binary VLE because we have a two component system, right? Benzene and toluene. So that's what these are called. And so there's actually, moving on here, there's actually some things that we can sort of interpret from these graphs, and that has to deal with what's going on inside, between these two curves, right? Where um, it's the equilibrium part, right? And so we'll go a little bit deeper into that, into this next part here. All right, so like I said, let's sort of talk about what's going on between these two curves, right? The dew pressure and bubble pressure curves. What's going on in that middle region, the two-phase region, so to say. And so, like I said earlier, what's going on is simply a equilibrium between the vapor and liquid phase. So let's draw out what I'm talking about here. So just to have a rough sketch of the graph again, right, we have the pressure. This is x1 or y1, whichever way you want to interpret the values of the bottom for whichever curve, right? And we had the bubble pressure being linear in a way, and then the dew pressure, something like that. And so, like I said, we want to look at some region within that two-phase region, at some point within that two-phase region, right? And I'll just give it some value for now. And so this value here ultimately could be called Z1, which represents the total mole fraction of component 1, right? So this is, remember, a closed system, so that value will stay constant throughout. And from that, we kind of want to figure out what percentage of this mole fraction is actually liquid and vapor, right? And so let's sort of come up with a scenario that lets us figure this out. And so, for example, um, let's say that we have a closed container, right, with a liquid and vapor equilibrium, like shown in our graph, right? And in this, we have a total of 10 moles. And just to stay consistent, we'll use benzene and toluene again. And we'll say that Z1 here is 0.4 moles. So inside this container, 40% of it is benzene, right? And we want to figure out now how much of that is actually vapor and how much of that is actually liquid. Right, so there are some equations we can sort of use to write, to solve this, right? So we can write some balances to start with. So what are those balances? So what are these balances? Well, we can sort of do a overall balance, right, for everything here. So we know that there's 10 moles total of benzene and toluene, right? So the total amount of moles must equal the amount of moles in the vapor phase plus the amount of moles in the liquid phase, right? So this is going to be our sort of overall balance of everything. And then to go a step further, right, we can do a sort of a balance for a particular species, right? So in this case, we'll use the first compound, right? So the mole fraction of the total moles of benzene will equal this the mole fraction in the liquid phase, not liquid, the vapor phase times the amount of moles in the vapor phase plus the mole fraction in the liquid phase times the amount of moles in the liquid phase. And so we get a balance for our per species, right? And so what else can we do now in terms of equations? All right, so what other equations can we use here? Well, remember, this is a ideal closed system, and the graphs that we've been following, that we've made, have all been following Raoult's law, right? So that's another equation that we can use. So remember, that's the mole fraction in the liquid phase times the pure component vapor pressure. That's equal to the vapor mole fraction times the pressure. And then obviously we can do this for species 1 and 2, benzene and toluene in our case. And then we also have this other value that's sort of defined usually for VLE calculations. And that's this K value. And that's simply the ratio of the mole fractions. And so we write it as this, vapor phase over the ratio of the vapor phase to the mole fraction of the vapor to the mole fraction of the liquid phase. And that's equal to the pure component vapor pressure over the pressure. And so usually for these calculations, we're given a we're given a temperature, so we can figure out the pure component vapor pressure, right? And most of the time, we're also given the pressure that it needs to be at. And so all of this work that we've done so far is sort of a super oversimplification of something called a flash calculation. And so let's sort of turn what we have right now into a proper flash calculation problem. And so I'll be doing that here. All right, so let's turn this into a proper flash calculation problem, right? So this F that I had written earlier is actually our total feed. So there's this feed that's going into something that's called a flash drum. And in that flash drum, there is a vapor liquid equilibrium that has occurred, right? And so we have a total feed. So I'll write feed here. That's going in at 10 moles per second. And so of that feed, we know that it has a component 1 is a 0.4 mole fraction. And so compound 1 is going into it at 4 moles per second, right? And from that flash drum, there are pipes that are taking out the vapor phase and liquid phase. And this whole flash drum is a closed system. And it's actually also being controlled. It's being set to some temperature and pressure that is within this two-phase region, right? So in our case, later on here, if you're looking at question 4 here, it'll be set at 393 Kelvin and 150,000 pascals. And so what we are trying to find from these flash calculations, right, are how much is in the vapor phase, how much is in the liquid phase, and of those vapor and liquid phases, what is the mole fraction of compound 1? And from that, we can also then figure out compound 2. So it's sort of implicitly stated then after we've solved these 4 things. And you'll notice that we've sort of already set up the 4 occasions we need for our 4 unknowns. And so what is the method that we would use to sort of solve these calculations? And that's what we'll be figuring out next here, the Rachford-Rice equation, which we'll be deriving. So let's derive this Rachford-Rice equation, right? So it actually starts off with saying that the summation of the mole fraction of the vapor phase minus the summation of the mole fractions of the liquid phase is equal to 0, which sort of makes sense. Which does not even sort of, it makes sense. 1 minus 1, 0. But anyway, we have 2 unknowns here that we can't do anything much with. And so we want to do some substitutions. And one substitution that we can do is using the K value that we had defined earlier. And since in our example the temperature and pressure is given as stated on screen there, we can use that substitution. And with that substitution, we can say that the mole fraction in the vapor phase is equal to their ratio times mole fraction in the liquid phase. And so then we can do that substitution. But first, I will simplify this. So that's yi minus xi, just combining the summations since they're starting from the same and ending. And then actually doing the substitution. And then factoring out the xi. And this is what we're left with. And so now we want to sort of find an expression or something that we can to substitute into xi this time around. And so using our other equations that we have created thus far, our per species balance equation contains xi, and so we can use that as a substitution. And so that equation was the total feed times the mole fraction of whatever component is equal to the amount of moles in the vapor phase times the mole fraction of that component in the vapor phase plus the amount of moles in the liquid phase times the mole fraction of that component in the liquid phase. And so from there, you can see that this per species balance equation actually has a bunch of unknowns in it, and we sort of want to decrease that amount. And so one thing that we can do is use that earlier substitution, and for this equation this time around, the yi equals ki times xi, and then we can also use our overall balance equation, which was the total feed is equal to the amount of moles in the vapor phase plus the amount of moles in the liquid phase. We can sort of rearrange that to solve for L, and then plug it in to this equation, which is then F minus V is equal to L. And so we'll do this double substitution now, which is then F Zi is equal to V Ki Xi plus F minus V times Xi, and then we can factor out an Xi, Vki plus F minus V Xi, and then we can factor out a V out of these two variables there. So then we're left with F plus V times the Ki minus 1 times Xi. And so then we can divide it over, and hopefully me adjusting the paper didn't move it out of camera. Plus V times Ki minus 1 is equal to Xi. And so then they then did a step here, which is not so obvious, in which they actually multiplied the numerator and denominator of the left-hand side here of the inverse of the total feed, so 1 over F. And that results in this here. And you are left with an interesting ratio within your denominator, V over F, right? But something over the total is simply the fraction of that something, right? Which is terrible explanation, but super generalized. But I'll reword it here for this example of what we have. So the vapor phase over the total feed, right? That is simply the fraction of the total feed that leaves as vapor, right? Which makes sense. If you had the vapor being divided by the total feed, right? That's just the amount that leaves as a vapor. So then we can now substitute this back in. Actually writing it correctly. Then substituting that into xi, we get this as our equation to solve for, then to use to solve for the other unknowns in our flash calculation that we had set up earlier, our specific example. And so this is what we will be using in Python to solve our flash calculation. So let's do that. All right, so let's code our Rachford-Rice equation, right, and solve for it. And you might also notice that I have customized my plotting here. I don't remember any of it, so I had to look it all up. So, and I sort of mimicked what my professor had. So there's that. So it was a lot easier to read. But anyway, back to the Rachford-Rice equation. So to begin with, let's just put in all our known parameters. So firstly, it's at 393 Kelvin. The pressure is at 150 1,000 pascals. We know our composition of their feed, right? That's 0.4 benzene and 0.6 toluene. We also know our total feed, which is 10 moles per second. And we also know our K value, which is, remember, the pure component vapor pressure at that temperature divided by the pressure. And that's about it for our knowns. And so let's make a function for this Rachford-Rice. And as you know from earlier, it's equal to 0. So that is indicative of a root solver that we'll be using to sort of guess our VF value to make sure that the summation is equal to 0. And so that's just where we're headed right now. So let's define our Rachford-Rice equation, right? So this would want a vector just because we're using the root equation, right? And we're going to pull out our VF from that vector. Oops, did not mean to do that. And we want to return that in an array. So it was the summation here of z times k minus 1 divided by, I'll put parentheses there, 1 plus VF times k minus 1. And just counting parentheses, make sure that's right. All right. And so now we want to use a root equation, right? So RR, and just some guess, so let's put 0.5. And we have our answer for VF, which is this down here. And so since we'll be using VF to solve for everything else, we kind of want to set it as its own variable. So we want to pull out the scalar value and then set that equal to VF. And so let's solve for everything else, right? So V, the amount of moles in the vapor phase that's flowing out, is equal to VF times F, because it's V over F, remember? Then we have X, because we'll actually solve it for both X1 and X2 here, was that expression that we had substituted in at the very end, which was K minus 1 divided by, it's actually just this portion here. Hopefully that's the correct amount of parentheses. I'll double check here. And then we have L is equal to just F minus V. And then we have Y is equal to K times X. And so we have solved our flash calculation. And here's that. So at the pressure that we have it now, the fact that this is a negative value kind of states that everything that's coming out would be vapor. I actually think there was a typo in the problem statement here, actually. I know it says 150,000 pascals there, but that's not actually in the two-phase region, so our entire calculation wouldn't actually work. And so I'm pretty sure that problem statement, my computer's lagging real badly, is supposed to be at 180,000, so that's actually in the two-phase region, so we'd actually get correct numbers. That makes sense that we'd only get vapor because there would only be vapor for the conditions that we set it in. And so once my computer catches up here, we'll solve it for 180,000. And we get some correct values here. So 5 moles per second coming out as vapor, 4 moles coming out as liquid, and then decimal points, obviously, and then their composition. Uh-oh. I have done something funky. So their compositions. Uh, Give me 1 second to figure out this here. All right, so I found my error. It was just that I had misremembered my expression for x. This was supposed to be z. So now it should be correct. There we go. So you can see here for our liquid composition that's coming out, it's mainly toluene, and for our vapor, it's quite an even mix here. And so that's kind of it for the flash calculation here. And so there's actually one more thing that we can kind of pull out from what we've done so far, and that something is called the lever rule. So I'll be explaining that, or actually, as a matter of fact, deriving that here in a bit. Right. So to sort of clarify before we go to the lever rule here, what had happened when I said it was a typo might not have been. He might have wanted us to clarify what was happening with that negative value. And that's right. With that scenario where if we did have 150,000 pascals, so we'd be right here in the vapor region. If we had set those conditions there, it makes sense that we'd only get vapor. And so if we were to test it in the liquid region, so let's say we're at 0.4, right? So that would be 220. If we were to set it so that it was all liquid and we were to look here, yeah, we'd get a negative value for that. We see that we get only liquid coming out. So yeah, it's not that we can't use the Rachford-Rice, but we can at least interpret some of the answers in a sensible fashion. And so let's talk about lever rule or lever rule. So so if we were to redraw our plot here, it won't be perfect. We had our 0.4. This was x1, y1, z1. This was here. Remember, we had calculated this, right? Earlier in our flash calculation. So we know our compositions for our benzene. And so if we were to sort of like draw this out, oh god, that is not to scale. So it's like 3 and 5. So this is, you notice that it's a straight line. Well, it's supposed to be a straight line. Um, and that's the whole premise on lever rule here. And so let's first derive it, and so I can better explain that this relationship sort of occurs and is backed up by some of the experimental data here. And so to get this derivation, we actually use our two balance equations that we had earlier that we had gotten from our flash calculation. And so F equals V plus L, and F C1 equal Vy1 plus Lx1. And we substitute our total feed for the moles of vapor plus moles of liquid into the per species balance equation. And so we get something like this after distributing. And now we want to move them across and around so that they're grouped together with vapor and liquid. So we get is equal to y1 minus z1. And then we factor, and we get this. And then we divide across here. And we get this ratio here, vapor to liquid. And so you can see that this difference is actually this here. And this difference is this here. And so this is the premise for lever rule, or yeah, lever rule. And so let's say, let's sort of figure out why it's even called lever rule. So let's say that we wanted to step into a two-phase region where it just hit, where it just made its first drop of liquid. So let's continue with 0.4 here. And let's say it's at this pressure. So 168, I'll just do 168. Okay. And then shift enter, shift enter, shift enter, shift enter, shift enter. So just from sort of drawing out, right, we would be right here. And if we were to do the same drawing, our, well, this isn't drawn perfectly enough, but let's pretend that our xi still continues over here. Our xi, our liquid composition, would be all the way over to where it hits the bubble pressure curve function line, right? And our y1 would actually equal z1. So in this case, this sort of makes sense, where our first drop of liquid we would have a super, so z1 would basically equal y1, right? So we'd have a super small value for our liquid, right? And a super large value for our vapor. So this makes sense because we're still in our vapor region, right? So this ratio would be greater than 1, which makes sense, which I keep on saying makes sense. And we can sort of see that here with its large value here and small value here. And this 0.2 is all the way to the left. And, well, if we were to, it would be right here, 0.2. And this is basically 0.4 almost. So it makes sense. The data is backing up with what we would see when drawing this. And so if we were to increase it, we've already sort of talked about this scenario here, where Z1 is kind of in the middle. We get an even volume to liquid ratio, and so that's sort of reflected in our values here. If we were to do 180 again, see if we get a super close value to 1. Let's say we increase it, right, all the way up to the bubble pressure. So we just formed our first bubble of gas, vapor, I mean, right? And so we should expect here, since Z1 will equal X1, super small value, way lower than 1. Of course, it looks like that for my drawing, but if we were to compare it to an actual graph, we'll get some reasonable numbers, right? So let's choose that pressure value to sort of back it up with what we've drawn here on here. If my computer can handle all that's going on. So 197. Put that in here. Hopefully click the right spot. All right. And yeah, we see that. See, if we were to look at this ratio, it would be way super close to zero, right? So 0.2 to 9.78, which makes sense, right? And so it's called this lever rule because as you go up and down, it sort of pulls in either direction in an equal amount of way, right? In a proportional way, not equal, I guess I should say, in a proportional way. And so that's sort of what would happen as you sort of increase the pressure with the same composition. And this happens with whatever z value you do. So if I were to say over here, even this rule applies no matter where, right? And so that's basically all that we can do here for our super simple example. So hopefully that was an enjoyable ride. So thank you.